Hi team, welcome to Wiggins Maths. In this video we will be looking at solving differential equations that are written in some form of context. Now these tend to be the most common exam type question for differential equations. It really checks if you understand the concept and what's actually going on within a problem. Luckily for us, there are only a few different scenarios that we could possibly be asked at this stage of our maths career. So let's have a look at some of them. But before we do, of course, do not neglect the formula booklet. There might be something useful in here. Okay, so example type 1, nice and simple. If this appears in the exam, it's high fives all round. It's just a differential equation. Okay, there's nothing to actually figure out here. We've been told the differential equation. We've been told a boundary condition as well. Okay, so let's go for it. Separate the variables. Done. Integrate. Done. Okay, so the next step is we're going to substitute in our boundary condition. We're told it plain and simply in this question. Okay, x is 60 when t is 0. I tend to make a little note of that as part of my working out. It shows the examiner that I'm in control. So ln 60 equals c, doesn't it, when t is 0. So let's now write this out in full. Cool, we're nearly there. The question says giving x in terms of t. At the moment we've got ln x in terms of t. So take exponentials of both expressions. And then of course, using our index laws, we know that we can multiply these terms together. So therefore, that's going to be like that. And e to the ln 60. Well, e and ln inverse is one another, so it's just 60. So therefore, our final answer is that. Lovely. So that's the, with a pinch of salt, the easiest type of differential equation in context. Whew. Okay, so this one, a lot more text. Okay, now a lot of the time the text is there to put you off. Okay, the information in here is pretty much already part of this differential equation. It's worth scanning through, making sure you're not missing any key parts. But generally speaking, all this text just means this here. And we want to solve it to show that. Show that are really great in the exam, because for example, if I'm struggling to show that, I can still do part B. I still get the marks for that. Okay, so let's go for it. Okay, so we've got a bottle of water in a fridge. Temperature of the fridge is that. That's where that +3 comes from, I guess. And we want to solve this, which is the rate of change of the temperature of the water. So, separate the variables. Done. Integrate. Lovely. We've picked up some marks already. Okay, so we want theta to be the subject. At the moment we've got this horrific term. So let's deal with it bit by bit. Negative, don't like it. Multiply both sides by -1. Exponentials of both sides. Okay, so I'm sort of going to make theta the subject here. So it's going to be negative. Okay, it is not far off what we want. Again, index laws, I can say this must be true. And this term at the front, negative e to the power of c, that's just a constant. So I'm going to give that a new variable. Let's call it a. You know, that's what they've used in the question, so it makes sense to do that. And then finally, is that what we want? It's not far off. Negative 1 over 125 is in fact negative 0.008t plus 3. Okay, so we've successfully shown that. A little bit tougher, but not too bad. Okay, and then as I say, part B now. Given that the temperature of the water in the bottle when it was put in the fridge was 16 degrees, okay, so what can we say about that? Well, we can say time t is 0, theta is 16, okay. So let's substitute that in to begin with. So 16 equals a plus 3. So a must therefore be 13. So that's a start. So now I can say that theta is 13e to the negative 0.08 t plus 3. Find the time taken for the temperature of the water in the bottle to fall below 10 degrees. So that's theta is less than 10 degrees. So let's figure out what time theta becomes 10. So let's do that. So 10 okay. So that's 7 over 13 equals e to the negative 0. Apologies for that, 0.008 t. So natural log of both sides. Divide both sides by negative 0.08 and you get t is 77.3799. So my answer is t is 77 minutes to the nearest minute, which is what it asked for. Okay, so both of those examples we were given the differential equation to begin with. Okay, on to our next type. Okay, so generally it is something to do with the shape. 3D object is more common than not. Been told lots and lots of what looks like complicated information in that text. This is where students tend to panic. Okay, but we can look at it in a slightly different way. We want to show that t minutes after the tap has been opened, this statement is true. Okay, so dH by dt is our sort of end game. That's what we would like to find. Okay, so let's write down some information that might be useful. So firstly, it's to do with the volume of the water, and we should know the volume of the water is pi r squared h. Okay, it's just the volume of a cylinder, isn't it? And we know that the radius of this particular cylindrical water tank is 3 meters. Therefore, V is 9 pi h. And actually, we can say that dV by dH is 9 pi. That's a pretty good start. Okay, we're also looking at the rate of change of water. So what else do we have? We have the volume is changing over time. And let's think about how much is changing. So the water is flowing into a tank at a constant rate of that. And when the tap is open, it's leaving at a rate of that. So that is just 0.48 pi is going in, and 0.6 pi h is coming out. So dV by dt, that's what the change of volume is. That's going in, that's coming out. So this is called a connected rates of change problem. It is the most complicated type of problem here. So remember, our aim is dH by dt. So it's going to be dH by something multiplied by the same something dt. Well, the only thing that we've got really is volume, right? So it's going to be dV in both of those. So we can now say that dH by dt is equal to dH by dV. Well, that's 1 over 9 pi multiplied by this rate of change. Okay, and then when we get to this point, we can sort of look at what we're trying to show. So that's 4 and that's 0.48 and that's 5 and that's 0.6. So actually, if I take a factor of 0.12 out, that's going to leave me with 4 and 5. There's no real sort of fast method for this. This is just down to experience, I guess. Okay, so that's going to be 4 pi subtract 5 pi h. But also look, we've got this pi that will cancel out. So then we've definitely got our 4 subtract 5h, which is a good start, a really good start. Now here's the really clever bit. 0.12 over 9 is 1 over 75. So then multiply both sides by 75. We get 4 subtract 5h. Whew. So that is pretty tough. Okay, and it will take a lot of practice, but it's definitely doable, and it's also a show that question as well, which is also worth pointing out. Okay, so the next part is find the value of t when h is 0.5, and we have been given this boundary condition, t is 0, h is 0.2. So now we can solve it. Okay, so let's separate the variables. Okay, I could have had the 75 over here, 1/75 over here. It doesn't really make any difference. It'll still be the same problem. Okay. So here we're going to have negative 15 ln 4 subtract 5h equals t plus c. Now let's chuck in our boundary condition. So t is 0, h is 0.2. Okay, so h is 0.2, then we're going to get negative 15 ln 3 is equal to c. So then our full differential equation is negative 15 ln 4 subtract 5h equals t subtract 15 ln 3. And then we want to find out the value of t when h is 0.5, so let's substitute in h is 0.5. Okay, so when h is 0.5 we get That's 2.5, so that's going to be 3/2. And then if we just tidy this up ever so slightly, so add this and then so add that together, so we're going to get so that will give us t is in fact it will be 15 ln 2. Whew. Nearly there, guys, I promise. Okay, our final question type. We are told nothing. We are told very, very little. There's no show that, there's no differential equation. It's not particularly obvious unless you really, really read this question carefully. So let's go for it. So a spherical mint has radius, it's placed in the mouth and sucked. 4 minutes later, its radius is reduced. Simple model. The rate of decrease is inversely proportional. Okay, let's almost think back to GCSE maths now. The rate of decrease. So the radius is changing over time, right? So the radius is changing over time. So dr by dt is proportional to the square of the radius. Okay, it's a decrease, so it's going down. So therefore that tells us that dr by dt is equal to negative, let's call it k over r squared. Okay, so separate the variables. Done. Integrate. Done. Okay, and now let's use our boundary conditions. Okay, we are told that at time t is 0, the radius is 5. So therefore 125 over 3 is equal to c. And we're also told that after 4 minutes, the radius is 3. So that would be 9 is equal to negative 4k plus 125 over 3. Now just got to work out what k is. It works out that k is 49 over 6. Okay, so now we're in a position to write it out in full. So r cubed over 3 is equal to negative 49 over 6t plus 125 over 3. Now the question did say we had to define our variables, so we should do that. So r is the radius in millimeters and t is time in mins. That's what it means by define your variables. Okay, it's no more complicated than that. Lovely. So part B, hence find the total time taken for the mint to completely dissolve. Give your answer in minutes and seconds to the nearest second. So we want the radius to be 0, don't we? So 0 is equal to and then when you solve that, t is equal to 250 over 49, which is 5.1 minutes, which is 5 minutes and 6 seconds. Done. And then suggest a limitation of the model. There are loads. Okay, there are absolutely loads of limitations here. You just have to think logically. For example, mint cannot be bitten. If you're like me and I have mint in my mouth, I'll bite it. Okay, if it bites, it's not going to work. Limited to 5 mins and 6 seconds. Okay, it goes longer than that. It's suggesting that the radius of the mint is negative, and that's not possible. Okay, it could be that mint does not stay spherical. There are loads, you just have to choose one. Okay, so that's it really. Remember, watching this does not mean that you instantly will be able to do it. You really need to practice this concept, really, really tough. Okay, the more you practice, the better you become, the more confident you'll become. If you found this video useful, make sure you subscribe, tell your peers. I'll be aiming to upload new videos each week to ensure that we are as successful as possible. And of course, remember, amateurs call it genius, masters call it practice.